Okay, let's dive into this. Have you ever just looked around at the physical world and wondered, what's really pulling the strings? Today, we're demystifying the forces of motion. We're going to map out the invisible hands that shape literally everything we do, from tossing a crumpled piece of paper into the trash, all the way to the orbit of the planets.
So think about this. Why does an object's motion change? I mean, we can easily describe how fast something is moving, right? Or whether it's slowing down or speeding up. But just describing it doesn't really answer the ultimate question of why it started moving in the first place, or why it stopped. That right there is the core mystery we're solving today.
And the answer to that mystery? It's force. At its core, a force is simply a push or a pull exerted on an object. But what's absolutely crucial to grasp here is that force is a vector quantity. That means it has both magnitude and a specific direction. You can't just have a generic push out of nowhere. It has to be a push towards something or away from something. And we measure this invisible push or pull in newtons, named of course after Sir Isaac Newton. Here is our roadmap for the explainer. First, the invisible push and pull. Then, touching versus distant forces. Next up, the battle of net force. After that, mapping the forces. And finally, we'll wrap up with a really cool real-world scenario, the skydiver's equilibrium. All right, section 1, the invisible push and pull, changing motion and shape. To understand exactly what a force can actually do to an object in the real world, let's look at its 4 main kind of physical superpowers. Forces can cause an object to start moving, stop moving, change direction, or even change its physical shape. So whenever you throw a baseball, pull open a heavy door, or, slam on your car's brakes, you are actively exerting a force that completely alters an object's current state. Actually, without force, every single object in the entire universe would just stay exactly as it is forever. Moving right along to section 2, touching versus distant forces, the invisible taxonomy. Now, what's really interesting about this slide is how we organize these invisible hands. Physicists actually divide all these pushes and pulls into 2 distinct camps, contact forces versus non-contact forces. It's pretty straightforward. Contact forces require actual physical contact to work. Like if you want to push a grocery cart, your hands physically have to touch it, right? Non-contact forces, on the other hand, act over a distance without the objects ever actually touching. It's just a really brilliant mental framework for classifying every single physical interaction you will ever encounter. Let's quickly break down these contact forces. We've got applied force, which is just your direct, everyday push or pull. Then there's friction, that stubborn force opposing the sliding motion of surfaces. We also have normal force, which we'll actually look at closer in just a second. Tension is the pulling force transmitted right through a taut rope. Spring force, well, that comes from a compressed or stretched spring. And finally, air resistance or drag, where the air is physically pushing back against a moving object. But I really want to pause on one specific contact force because it is literally happening to you right now, and that's the normal force. By definition, it's the perpendicular support force exerted by a surface on an object in contact with it. Think about your current state right now. You're probably sitting in a chair, right? Gravity's pulling your mass downward. So why aren't you just falling straight through the floor? Well, it's because the chair is actively pushing up on you with a normal force that is exactly equal to your weight. Okay, now let's look at the non-contact forces, which are also known as field forces. As we said, these act at a distance. You've got gravitational force, magnetic force, and electric force. The big one we experience constantly, obviously, is gravity. Earth's gravity is pulling downward on every single object with mass, creating a constant downward acceleration of about 9.8 meters per second squared near the surface. Notice, there are no physical strings attached to you pulling you to the ground. It's just the invisible, non-contact pull of mass. That brings us to section 3, the battle of net force, when forces collide. See, real life isn't just one pristine force acting in a perfect vacuum. It's more like a messy, dramatic tug of war. And that introduces us to net force. The net force is the vector sum of all the forces acting on an object. Because forces are vectors, remember, you can't just add their numbers together like simple math. You absolutely must strictly take their direction into account to find out the combined effect, or the resultant force. Basically, you have to see who wins the tug of war. So the crucial point is that forces in the same direction add together, while forces in opposite directions partially or fully cancel out. Imagine you're pushing a heavy box to the right with 10 newtons of force, but the floor friction is pushing back to the left with 3 newtons. They partially cancel.
So the net force, the actual resulting push the box ultimately feels, is just 7 newtons to the right.
But what happens if those opposing forces are perfectly equal? Let's say a 5 Newton push to the right and a 5 Newton push to the left. Well, you get this number, 0 newtons. This right here is the magic state of equilibrium. When forces perfectly balance each other out, the net force is 0. And when the net force is 0, the object does not accelerate. If it's sitting still on a table, it stays perfectly still. If it happens to already be moving, it just keeps moving at the exact same constant velocity. A net force of 0 means absolutely no change in motion. Now for section 4, mapping the forces, your universal decoder in.
You might be wondering, how do we possibly keep track of all these competing pushes and pulls? Well, we use the single most important problem-solving tool in all of physics, the free body diagram. It's a really simplified drawing showing an object as a dot, with arrows representing all the acting forces. Professional engineers literally rely on these daily to do things like design aircraft wings, calculate bridge loads, and even plan spacecraft trajectories. By visually isolating an object from its messy environment, you can decode exactly what forces are controlling it.
And creating one is actually incredibly simple. Step 1, draw the object as a simple dot or a box, just stripping away all the visual distractions of the real world. Step 2, identify every single force acting on the object. Step 3, draw arrows originating from the center, pointing in the exact direction the force acts. And here's a pro tip, the length of the arrow visually represents the magnitude of the force. A stronger force gets a longer arrow. Finally, step 4, double check that you've included all the relevant forces. All right, section 5, the skydiver's equilibrium, high-stakes physics. Let's move to this and see how it builds on what we just learned. We're going to apply our new free body diagram superpower to a very dynamic, high-stakes situation, a person falling from the sky. Picture a skydiver jumping out of an airplane. Initially, gravity is the undisputed dominant force, right? So the skydiver accelerates downward very rapidly. But eventually, as they fall faster, the air resistance pushing back up against them increases until they hit a point where they reach a constant speed. This is known as terminal velocity. They completely stop accelerating, even though they are still plummeting toward the Earth at an absolutely incredible speed. So, based on everything we've covered today regarding equilibrium and moving objects, ponder this for a second. What must be true about the forces acting on the skydiver at terminal velocity? Comparing the stages side by side really reveals the underlying physics here. Look at the initial fall stage. The acceleration is rapid and downward, meaning the net force is strictly non-zero and unbalanced. Gravity is definitely winning. But at terminal velocity, the acceleration drops completely to 0 because they are moving at a constant speed. And remember, 0 acceleration strictly means 0 net force. So the forces have suddenly become perfectly balanced right in the middle of a massive fall. And this completely resolves our skydiver mystery. At terminal velocity, the air resistance pushing up against the skydiver perfectly equals the gravity pulling them down. The forces are entirely balanced. If you drew a free body diagram for this exact moment, you would draw your dot for the skydiver, an arrow pointing straight down for gravity, and an arrow pointing straight up for air resistance. And both of those arrows would be the exact same length. They effectively cancel each other out, locking the skydiver into a state of dynamic equilibrium. Which brings us to our final thought for today's explainer. What invisible forces are pushing, pulling, and perfectly balancing to shape your exact physical state right at this moment? I want you to look around your room right now. Look at your computer monitor, your coffee cup, the chair you're sitting in. Try to mentally draw the invisible, free body diagrams dictating their reality. Because once you start seeing the forces, you realize they truly are the invisible hands holding the entire universe together. Keep mapping out those forces, keep questioning how the physical world works, and we'll see you in the next explainer.